first and let me start the class for today. Okay. So, is my screen visible to you? Okay. Okay, let's start. Okay. So, till our last class, we have discussed the topics like value iteration and uh, uh, how the value iteration could be executed using Bellman's equation, and those things we have discussed till our last class. Now, today, what we are going to start with is policy iteration. There is one topic left that I have not discussed, that is and that is that how the convergence is being executed during value iteration, or the how can the convergence be assured. You need to study it by. Okay, I have not discussed it here. I am starting with policy iteration. Now, you know that policy is the set of actions that we know we are going to execute in each individual state. Okay? So, if one action that is given a set of action, if you remember that in our last class, while computing the Bellman's equation, we have executed a maximization operation over max operation over all the possible actions in the state. Okay? So over that we have maximized the utility. Okay. Now you know that if one action is strictly producing some better result, then the action should be preferred over the other action. That is, if we are having such an action that is maximizing the utility. Okay. Now, therefore, the exact utilities of the states need not to be predicted. The fact is that we don't always need to predict the exact utility value. But what we can do, we can just move closer to that exact utility value. Okay, so that technique, or that is moving towards the exact utility value with optimal policy, is a part of policy iteration algorithm. So that part is called policy iteration. If you remember, in the last class, we have discussed about value iteration, and there the values of each state, the utility values of each state is being computed by converging that with the convergence of, or with when the utility values of a state between consecutive iteration are not changing more than a given threshold. Okay, so we have computed the value iteration like that. Now, in case of poly iteration, what we are going to do, what we need to compute. We are given with a policy. Given a policy by we need to compute the utility of that policy. Okay. That is, so we need to compute the utility of the policy. So this is called, actually this technique is called policy iteration. Now, how can the policy gets improved, or what is the underlying principle for policy improvement? So how we are going to compute the improvement of the policy? Are going to compute a new maximum expected utility of the policy in the next iteration. That is pi I plus 1. For pi I plus 1, we are going to compute the MU, and using that, we are using a one-step look ahead based on UI. Therefore, we are going to a new MEU I plus 1. This is what we are going to compute. Okay. Now, by we are going to compute it because we are using a one-step look-ahead method. That is, we are we are computing the policy for the next iteration. Now, with this, what we are gaining or what we are having? We are having a simplified version of Bellman's equation. How we are going to get a simplified Bellman's equation? It is like here U is equals to, it becomes equals to R of S plus S bar P of S bar for S. Now, compared to the Bellman's equation that we have used for value iteration, okay, this Bellman's equation is a simplified version of it. Can you say why? What is the difference between these two Bellman's equation? Why this Bellman's equation can be called a simplified Bellman's equation? Can you say? Anyone? What is the difference between these two equations? Good, Mr. Durgesh, you are exactly right. That is, this equation is a linear equation. Here we are not using any max operator. Max operator was non-linear, and here we are not using a max operator because we do already have an optimal policy in the ith iteration. Okay, so we do, as we have a policy, we know that which action is to take in the state S. Therefore, we don't need to compute the which action actually maximizes this term. Okay, instead of performing it for each and every possible action in the state S, we, since we have a policy, we know that which action is to be executed in the state S. Okay, therefore we are here omitting that max operation, and this is how this Bellman's equation becomes a linear one. Okay. Now, if we see the example, similar example, then if you remember in our, yes, this was the policy that we have executed. Let's see over this policy or over this example how we are going to compute those utility values using this updated Bellman's equation. Okay, so let's see. So this is the example that we are discussing with, and here we are going to give the example. Now, if you are going to compute here, say U I 1 1, how you compute it? What you are going to compute it here? UI 1 1. Let's from here to say here. Now, how you are going to compute UI1? It will be equals to minus 0.0. And now you know the action. At 1, 1, you know the action is up. Therefore, whatever you are going to compute is against the action up. Okay. Therefore, you know it is according to the policy. Okay. So it is going to be 0.8 into U I U1 plus 0.1 into UI 1 plus plus 0.1 into U 0.1 into UI 1. So this is how we are going to compute UI11. Okay. Now, similarly, you can compute UI12. Can you compute it? Given the policy, that is UI12 is going again against the action up. Okay. So in the policy, the desired action is up. Now, you can also compute UI1. Therefore, for a large space now, for if you have policy and therefore simplified value iteration steps become like that. That is how you are going to have some simplified value iteration steps, and the value iteration steps will get simplified, and we will have the following equation, that is UI I plus 1 is is R is plus comma is E of is bar over is Y is mm, so this is how we are going to have a simplified uh, value iteration step. Okay. Now, policy iteration, there is an algorithm where the inputs are the MDPs and the MDP, which is a MDP, that is Markov decision model with Markov decision process with ACE states. ACE is the action and the transition. Here, what we are going to we are going to do assign the initial policy to some random numbers, and similarly as that of similarly like that value iteration algorithm, here we are going to compute the policy for each state is, and we are going to check whether the policy at state S gets changed with iteration. Okay. So this is how we are going to uh, compute our policy for the state S. Okay. So now let's move to the today's very important topic, that is partially observable MDP. We are familiar with as of now, we are familiar with Markovian decision process. Now, what we are going to discuss is that partially observable Markovian decision process. In short, these are called POMDP. Okay. So we are now going to discuss about POMDPs. Now we have discussed MDPs, and we know we were given with the following inputs. That is, we know which state the agent is currently in. We know what possible set of actions, or we even know the policy. Okay, and we also know the transition model. That is, upon taking action A, to which state the agent can go. Okay, from A to which state the agent can go. The transition model is also with us in case of MDPs. But in case of partially operational MDP, how is it different from MDPs is that is here the less number of things are known. Okay, it is partially observable because the current state is not always known to the agent. That is, if it is known, then it will become a MDP. But the fact is that it is called partially observable because the current state is not always known to the agent. Now, if the agent does not know its current state, will there be any impact if, even though the agent knows its policy or optimal policy? Is it going to have any impact? Knowing the optimal policy does make any difference if the agent does not know its current state? Is it going to make any difference? I'm asking you. You can respond me. What do you think? If the agent does not know which state it is currently in, yes, it doesn't. It is not going to be. Yes, Mr. Manush, why you are thinking that it is going to make some difference? See, we can decide the policy or optimal policy. Given the optimal policy, we can decide which action to be taken in state or to be executed. Okay, if you don't know which state you are currently in, then how can you decide that which action you should take, even though the policy is given to you? You don't know your current state, therefore you won't be able to take the decision on the current state. Okay, so that is why the even though the policy is given, it is not going to make any impact. Okay, therefore here actually what are given to the agent? Here the agent is given with a transition model. Transition model is provided. Okay, transition model means that is P of is bar given is A. It is given to the agent. Okay, then set of actions are also given. Set of actions, that is A of S, that is given to the agent. Okay, and reward function is also given. Reward function R of S is also given, and a sensor model. That is the most interesting part, and this is how it differs. Sensor model is P of E over S. This is where the difference lies. Let's highlight it. This is where the difference lies. Okay, so here instead of the current state, we will have some observation about the current state. Okay, this is where it differs from conventional evidence. That is, well, let me discuss a few things about this observating states. Okay, what are those? Did you know Bayes network? Did you know Bayes net? Okay, that's good. Now, the fact is that in Bayes network, what we are doing, we are observing something and we are computing how much probable to for an event to occur. For example, you know Bayes network very well. Therefore, I am just giving you an example that, for example, you don't know whether a day can be sunny or rainy. Okay, but you know that if it is rainy, you can see people around you that they are using an umbrella while they are going outside. Okay, but it is also the fact that even though it is rainy, even though it is a sunny day, then also it is, although it is less probable, but there is non-zero probability that the people that someone is using an umbrella. Okay, therefore, if you see a person to use an umbrella while going outside, what is the probability that it is raining outside? When observing that event, that is whether the person is taking his umbrella with him while going outside, you are going to compute the state, the actual state, that whether it is a rainy day or a sunny day outside. You don't know that, but you are predicting that or you are computing that. This is how Bayes network works. That is, given the event, what is the possibility of the state? Here also, you have the sensor model. That is, you have some observation from which you need to conclude that which state the which state that agent can now be. Okay, what is the current state of the agent? Given the observation, you need to know. So this is what the sensor model is doing. So now the fact is that we are assigning a belief state, that is belief state is, that is, probabilities assigned to the actual state is by the belief state. That is, if you see a person is taking umbrella, you can say that there is 90% probability that it is raining outside. Okay, so this is the belief state. That is, probabilities assigned to the actual state is by belief state B. Now, if now how you are going to compute the future belief state? Okay. Now, if or the current belief state, if the B is represents the current belief state or previous belief state, B represents the previous belief state previous belief state, and A is the action and E is the evidence. Okay. So what is that? That is, you are assigning a, now how you are going to compute the new belief state from the previous belief state. How you are going to compute it? You are going to compute the new belief state given the previous belief state using the following equation. That is, B bar is bar is equals to alpha into P of E over S bar sum is P. So this is how you are going to compute the new belief state from previous belief state. Alpha is a normalizing constant that sums up the belief state to 1. Okay? Sums up all the belief state to 1. Now, the fact is that B bar actually is, say, that B bar actually is a function of a forwarding function. Forwarding function of B, A, and E. Okay. So this is what B bar is. B bar is a forwarding function of B, A, and E. Now, if you need to understand a POMDP, the optimal action that depends only on agent's current belief is to be known. That is, and this is how we are going to compute the optimal policy only based on the belief. Okay. So in case of POMDPs, we are going to compute the optimal policy based on the belief, not based on the state, not based on the actual state. Okay. So there is a decision cycle for POMDPs. Let's see how the decision cycle is being executed. It is given current belief B, execute action A equals to receive set E set current belief, that is forward function of B, A, and E. And repeat. So this is the decision cycle for a POM. Okay. You need to, as we have already discussed, that we don't have the current state, therefore we are setting the optimal policy over our belief. Now, by setting that optimal policy over our belief, we are executing an action and we are receiving an observation or percept E. Okay. Then with that forwarding function, that is with B, A, and E, we are setting our current belief. We are updating the belief and we are repeating the entire process. So the agent does not know the current state. It does what it does have is a belief. As I have already given you the example that you know that you don't know whether it is raining outside or whether it is a sunny day outside, but you are seeing that a person is taking an umbrella. Okay. Likewise, with that observation, you are assigning a belief that there is 0.9 probability that it is raining outside. The probability that you are assigning to the current state is called belief, a possible state. Okay. Sensor model is something different. It is not giving you the, it is not showing the photo of outside. The sensor model here, in the example, okay, it is not the sensor you have not, it is not some camera that is fit outside and be sitting inside, you are viewing that whether it is sunny or rainy in the outside. This is not the sensor model. Sensor model is that whether the person is taking the umbrella or not, or keeping it. This is the sensor model. Okay. So with the sensor model, you are going to have only partial information and with noise. That is, even though the person not taking the umbrella, there is also non-zero possibility that it could be raining outside. Okay. So this is why actually. Now, the fact is that the belief state actually changes with action. Okay? And value of information here is very important. If you remember that we have discussed, we already had a discussion about value for information, and here, especially here, the value for information in POMDP models are very important. Okay, any information, the sensor value and all those things, they are plays very important role in case of POMDP. Now, what is the probability of getting E? Okay, what is the probability of receiving that observation E given A was actually performed, given that A was actually performed by summing up all the step is bar. So what is the probability of reaching B bar from that is, what is the probability of having A given A and B? Okay, so let's try to define it mathematically. If you want to define that, what is the probability of receiving E, receiving the observation after executing action A and having a belief B? What is the probability of receiving it? It is equals to, hello, can you listen me? Okay. So what is the probability of having, of getting that observation? It could be expressed as probability of E of A, comma, is bar, comma, B into probability of is bar given A and so this is a mathematical expression that we can mathematically express. Now this is going to be equals to sum of is bar probability of E given is bar into probability of is bar given A comma E and A comma B, and it can also be expressed as is bar P E over is bar sum of is P is bar over is comma A B is. Therefore, it is actually how you can compute that what is the probability of having an observation E upon executing action A and having a belief state B. Okay, so this is how you can compute it. So this is the equation that you can follow. Now, then again we are going to compute another thing, that is what is the probability of having B bar given state B and action A. So what is the probability of having B bar given state B and action A? How we are going to compute it? It is equals to, then how we are going to compute it? It is equals to, we can easily write it as probability of B bar given action A, and you can interchange it, and it is going to be equals to sum over all evidence of probability of B bar over E A B. Probability of E over equals to So this is how you can ultimately have that what is the probability of having B bar given new belief. Yes, B bar is the new belief. And what is the probability of reaching to B bar from B given action? This is how you can compute. Okay. This is the equations that you can follow. Now, there is what is the reward function of a belief state. How can the reward function be computed? Reward function of belief state. Okay. So how can it be computed? It is denoted as rho B and it is equals to sum of A's B A's R A's. Okay. So this is the reward function. Okay. So this is the reward function of against a belief state. Okay? So this is the reward function of a belief state. And now if you see that these two things, that is you have a reward against the belief, you have a transition model against the belief. Okay. When you are having these two things, you can say that this model, that the POMDP model has been converted into a MDP over that belief state. Okay, that is, you are given a transition model over belief state. You are given a reward function over that belief state. Therefore, now you can say that you have everything over the belief state instead of the actual state. Therefore, over the belief state, that model has been turned to be an MDP instead of POMDP. That POMDP has been turned into an MDP over that belief state. Okay. So, excuse me. So these are the things. Now, let's discuss another thing that is called dynamic decision network. Okay. Did you have any idea about dynamic Bayes network? Well, you don't have any idea about dynamic Bayes network, but you know the Bayes network. Okay. So now let me try to give you some idea regarding dynamic Bayes network. Now you know, in case of a Bayes network, there exists some observation state. There exists some hello, someone's microphone is on. Hello, I don't know whose microphone is on, but whoever whose microphone is on, please switch it off. Mute it. Now you know that you have some observation state. Let's see, for this example, we can say that we have an evidence. We have some actual state that is denoted by x of t. Okay. Now, as we know that the ET is actually the outcome of XT. And we can only observe this ET from which we are going to take the decision regarding the observation X. Okay. Now this is our base network, and we are given with some prior probabilities that what is probability of occurring ET individually, what is the probability of occurring XT individually, and what is the probability of occurring ET given XT, all those things we know. Okay. Therefore, we are going to compute what is the probability of occurring XT given ET. So this is what we are doing in our base network. But here we have another things to decide, that is which action to be taken. Okay. And we are taking the action in our previous state, that is in, you can say in A t minus 1, we have taken some action due to which we have reached to the state xt. Okay. So in the previous instant, we must have taken some action, and due to which we have reached to the state xt. Now, the fact is that when you are adding some time axis here, it is becoming a dynamic base network. That is, whenever you are going to assign some transition models, that is, say it becomes your previous instant t minus 1, and it becomes your some previous instant t minus 1, it is t minus 2, and it is xt and et. There exists some relation between these two transition states. So these two states, and accordingly you are going to take some decision in this state, as a result of which you are going to have xt minus 1. So here you are going to take a t minus 1, which will result you in a state of xt. Okay. If your network looks like this, and it will have many more components here also, like xt plus 1, xt plus 2, like those, you are going to have many more components here. When the network looks like this, and similarly for xt minus 2, t minus 3, there will be another decision. If your network takes a shape like this, that is, you are going to predict those probabilities from, given this information, you are going to predict the probabilities of the future states. Then, or you are going to predict the future states. Then your network is becoming a dynamic base network. Okay. It is a very simple example. Let's say this is a sunny day, and you know that this is a rainy day, and you also know that the evidence, you can observe the evidence that it is an umbrella. Here you can observe it is also an umbrella here, and you are going to predict that how much likely it is to be a rainy day. Then the information that you are going to have, not only excuse me, not only the prior probabilities but also the transition models. The prior, except the prior and conditional probabilities, that information you are going to incorporate is a transition model. That is what is the probability of a rainy day being followed by another rainy day? What is the probability that there could be two consecutive rainy days? Given that you know that the previous day was a rainy day, and there was umbrella seen there. Today you are also seeing an umbrella. Then how much likely it is that today is also a rainy day? How much likely it is? Okay. Therefore, here you are going to here actually you are going to uh, take into account that what is the probability that two consecutive rainy days can occur. Okay. So whenever you are inducing that transition model into that Bayes network, it is becoming a dynamic Bayes. Now here we have used that dynamic Bayes network to compute our utility and to how we have represented it here. You can see that here these informations, that is the information in the dark regions, are known to us. We know what actions was taken in the instant t minus 2. We know how much reward we have received in at t minus 1, and this is the evidences. Okay. Now these are only the known. We have no information about the actual states. We are only going to predict that actual state, that these are the models that are given to you, that upon taking action a minus 2 and given evidence et minus 1, what is the probability of reaching xt minus 1, and all those things we are given. We are going to predict it till xt t plus 3, and after that all the reward values are summed up as the utility of t plus 3. Okay. Now, once and if you remember those decision notes or the decision diagram, here these are represents, that is the observation, that belief states or observation, and the current states are represented as the chance node of a decision maker. Okay, and the actions to be taken are represented as the decision node, as the decision network, that is in a rectangular shape. These are represented in an oval shape, and these are the utility nodes, that is a diamond shape, that is reward functions are represented as the utility nodes. Okay, so this is how in the form of a, this is actually a combination of dynamic Bayes network and a decision network. Okay, so this diagram is a combination of, or this type of representation is a combination of dynamic Bayes network and decision network, and that is how it is known to be a dynamic decision network. Okay, so this is actually it is, if you go through these things, I think it will be much clear. You have to study the things, otherwise the things won't be clear. We are already lagging behind the time. Let me discuss a few more things here, that how can you use that look ahead. Here the part of the look ahead solution of decision dynamic decision network is given here. Here the triangle shapes represent the belief state in which the agent makes decision. Okay, so the triangle shape are the states where the agents are making some decision, that is the belief states, and the oval ones are the chance nodes where the evidence arrives. Okay, now here what happens is that no chance node in action, no chance node in action, the belief state update corresponding certain action is deterministic, and given a belief state, given this belief state, there are a number of possible chance nodes, that is these are the evidence that could arrive, and from that evidence again you can have this actions, that is in this belief state there could be anything another action in the next instant time instant, that is xt plus 1, and here the observations varies from 1 to t plus 1 and 1 to t observations. You are having those set of observations based on which you are going to predict the current state or the future state, here the future state, that is t plus 1, and you are also going to decide which action to be taken in that state. By taking that action you are again reaching or you are again receiving a set of observations, that is et plus 2 in the et plus 2 state, and likewise you are continuing. It is a look ahead solution for dynamic decision making. Okay? So this is the thing. Now what is the how those belief states and uh, belief states can be computed. Belief state can be computed with filtering algorithm, and for the decision against the action at t plus I, the agent will have available percepts t plus 1 to t plus I. Okay. Now decision can be extracted from the search tree by backing up the utility values from the leaves. So how we are going to take the decision? Here we are going to have the utility value and we are now backing it up, and we are going to take that how to maximize that utility value upon which actions. Okay. So if we back it up here like that, and we can maximize the utility value and we can decide that which action is to be taken. What is the advantage? There are some advantages and disadvantages of this dynamic decision network. That is, dynamic decision networks are handled in partially observable uncertain environments. Therefore, it actually easily devise their plan for unexpected evidence. Okay? If some unexpected evidence occurs, it can revise the plan. Since it is a backup approach, we are looking from the future to the back. Okay? Now, here another advantage is that if there is any sensor failure, that also could be handled with appropriate sensor model. Therefore, it actually, in other words, also called the terminology is used, that is called wasteful degradation, that is exhibited under this complex and various approximation techniques. And there also exists some defects of this DDN, that is dynamic decision network. That is, since it relies on forward search through state space rather than hierarchical, it relies on the forward search through state space rather than hierarchical plan. Okay. So this is the advantage of disadvantage of it, and you have to go through the things well. I have just gisted it. Okay, I have just gisted it of what wasteful degradation is. I have just listed the things, but you need to thoroughly go through it once again. There, only this way you shall be able to get the entire things. Okay, so this is all for today. Now we shall discuss the quiz quickly. And please remember, well, I have to ask you that yes, I have to ask you that tomorrow is the last class. It's supposed to be the last class of this fractal, and tomorrow I am going to discuss the decision making with multiple agents. So far, whatever we have discussed is all the decision making was done with a single agent. Now we are going to discuss how the decision making will be done if multiple agents are present there. And in other words, that is called to be game theory. Okay. So game theory I am going to discuss you in tomorrow's class, but generally it takes around 3 to 4 classes for me, regular classes, to finish up game theory. Now it is up to you. If you say that whatever I am going to discuss, I shall only be able to discuss, I think, half of that part, half of the game theory in tomorrow's class. If you are ready to study, to conduct a self-study for the rest of the content, it is all right for me. But if you ask me to teach the rest of the content, then I need an extra class for you. Okay? So it is your decision that what you would like to do. You please let me know what shall I do. Should I discuss the things and half of the things and leave the rest for you for your self study, or should I discuss the entire things by conducting an extra class? What is your decision? Just let me. Okay, so you are ready to have an extra class. Well, no issue. Then I can arrange an extra class according to your convenient time. Since next week is supposed to be a holiday, I can take an extra class in the next week too, if you wish. Yeah, the extra class will be without quiz. Yeah, there will be no quiz in that extra class. You don't need to worry it. But the fact is that I need to conduct that extra class, and if you agree, I can conduct that extra class in between the week. That is from 5 to 6:30, 5 p.m. to 6:30 p.m. in any weekday, if you want me to take the extra class. Or alternatively, I can take the extra class in the next day, that is a holiday, on the next Saturday. It is supposed to be a holiday for you, but if you agree, I can take the extra class. Weekdays are not possible. Okay. Then I shall conduct the extra class on the next Saturday itself. Okay. In the scheduled time. So that is going to be the extra class then. And tomorrow onwards, tomorrow I am going to start the discussion regarding game theories and all. And that is the end of your syllabus. Actually. That is the last topic left here. So if you have any doubt and queries on whatever we have discussed till today, please let me know. Okay. Now let me discuss the solution of the quiz. You know that for calculating the utility state sequence, assume that agent's preference, that coherent ways of assigning utilities under stationary sequences. There are two coherent ways. One is by computing additive rewards, and another is by computing discounted rewards. So these are the two things that you need to mention. Now, how many fixed point can how many fixed point can contraction have? It should go to convergence. Therefore, there should be only one contraction. Now, if the environment does not contain terminal state, how can the utility be finite with all those things? With discounted reward, with a policy that guarantees to reach a terminal state, and by comparing it to average reward per time step, with all those things, it could be computed. It could be finite. Distance between utility vector, we will max norms measure the length of the vector by the absolute value of the biggest component. Okay. Now, the reason for going iterative approach in Bellman's equation, having n is n possible state would be uh, why we are going for that iterative approach is because the equation is non-linear, as we discussed it last class. When the discounted reward is considered, you want to share me the filled quiz copies. Okay. So when the discounted rewards is considered as additive reward, copy of your response. Unity is positive. For which you are saying that it should be one. Is considered as additive reward, it should be one. Discounted factor, it should be one. Discount factor is always positive. Discount factor is never negative. Please remember that. Discount factor is always positive. It always lies between 0 to 1. Okay. So while calculating the unity of state sequence stationary, if states are equal, then the both states start with the same sequence, that is S not equals to P. Okay. So these are the things, and then you need to write down the Bellman's equation, and it's a shortcoming. There is a non-linear equation, how the value equation could be derived, and all those things. So you need to write down those things here. So if it does always have a finite value for discounted rewards. Utility could be infinite if what is the shortcoming? Well, shortcoming is that it is a nonlinear equation and it is much more complex. Means the complexity is more for solving the equation. Okay, these are the shortcomings. So these are the things. Now, one of the question was related to this. Yes, one of the question was related to this. There is no issue. You can again rewrite that. So these are the things, and if you face any difficulties or doubts from whatever I have teach you so far, you can ask me via mail. Okay, so that is all for today, and again we will meet tomorrow. Okay, so have a good day. Bye. Thank you. Practice question and solution. Um, you can practice it from the exercise of your book itself if you want to. There is no other practice questions. You can practice it. Okay. Thank you.